Hello and welcome to a new recording on support vector machines. In this recording we are going to discover the mathematics behind the algorithm. It's wonderful to implement the algorithm, but it is even more wonderful to understand the mathematics that make this algorithm works. So let's get started. So in the beginning we have two vectors. We've got vector of sample 1 and a vector of sample 2. That vector, the first one, belongs to the first class and the second one belongs to the second class. So if we extend the vector from the 0 point over to each sample, we get two vectors like this. This one is y1, this one is y2. So y in our case takes two values. If the sample belongs to the first class, then y would be 1 minus 1. If the sample on the other hand belongs to the second class, y will be plus 1. So our target here is to maximize the distance, the hinge loss between these two classes. So from linear algebra, we know that if class 1 is represented, y1 equals omega x1 plus p. And then we've got y2 equals omega x2 plus p. We know that y1 equals minus 1 and y2 equals plus 1. So this is the line equation. This from elementary algebra. We know that the line has the slope omega and the intercept b. We subtract the two vectors to get the difference, so that will become omega x1 minus x2. Note here that we have got omega as a common factor, so you simply apply a minus sign over here, and over here. So you subtract element-wise subtraction, you get omega x1 minus omega x2. We take the omega as a common factor and then remains x1 minus x2, which is the target distance over here that we are trying to minimize or to maximize. And then the b will be eliminated, and we have got here minus 1 will become minus 2. So let's slip the equation to get x1 minus x2 on the right hand side, and then our equation becomes minus 2 over omega. So this is our objective function. The objective function in this case, we are trying to maximize minus 2 over omega. It is equivalent if we said that our objective function is to minimize we will flip this over. The inverse will become minus 1 over 2 omega. For convenience and to make this form to a form that we are familiar with and we can solve using linear algebra, we will apply a squared over omega so that it's close to the form of the quadratic programming. So this equation becomes minimize is equivalent to minus 1 over 2 omega squared. So this is our objective function. What about the constraints? This equation will be subject to the following constraint. The constraint simply in literal English would be that every sample in our dataset is classified correctly. That means for every sample that belongs to the first class, our equation should yield a -1 value, every sample that belongs to the second class, our equation should yield a +1 value. How can we represent that? We would say that omega xi plus b should be greater than 1 for every class that belongs to the second class. How about the other one? How do we get the negative one? We know that the classification is a -1 or +1. That means y of I will either be -1 in the first case, +1 in the second case. That's why we can simply multiply y of I on the left hand side. This gives us our equations. If y of I is +1, the equation goes this way. If y of I is -1, it goes the other way around, with -1 on the other hand side. So this is our objective function, this is our constraints. We still can't solve this equation. We will have to convert this from the primal form to dual form. And to do that, we have to use Lagrangian multipliers. It's quite a common and familiar algorithm. If you are familiar with any mathematics of machine learning, you will find that quite handy, quite useful in many math derivation of machine learning. So what does it say? Lagrangian multiplier says that the objective function is the old objective function minus some coefficients multiplied by the constraints. So remember, in the constraints here, we have got the I here that goes from I from 0 to n, where n is the number of samples in our data set. Let's do the substitution. L becomes our old objective function. Let's drop the negative for convenience. Half omega squared minus. So to do this for the range from 0 to n, that means we sum over I to n alpha of I, and then the constraint, and again for convenience let's bring the one on the right hand side. So this equation becomes y of I multiplied by omega x of I plus b all minus 1. Let's simplify this form. Alpha of I, y of I, omega x of I, and then again alpha of I, don't forget that we've got a minus here, alpha of I, y of I, alpha of I, y of I, b, and then negative negative is plus, sum over I, alpha of I. So this becomes our new objective function according to Lagrangian multipliers. Then we need to find the constraints, the new constraints. How do we find them? According to the Lagrangian rule, we have to get the first derivative of the objective function to the parameters of our equation. So we do the first derivative of L to the parameters of the equation we are trying to minimize. So what were the parameters? The parameters in our case were the parameters of the line. They support the vector separating the two classes. The vector or the line is defined by omega, the slope, and the intercept. So we do the first derivative relative to the slope omega, and then we do it once again relative to the intercept. Let's get it done. So here omega, the derivative of half x squared or x squared is 2x. So just as same in the case of a single variable, the case in a vector, the derivative of a vector will be 2 omega. 2 by 2 is gone, and then we have got omega remaining. Here we get the variables where omega appears. So this one and this one become 0. Here it becomes the coefficients of omega. The derivative of 2x is 2. The derivative of 2 omega is 2. Here our constants are alpha, y, and xi. So this becomes negative sum over I, alpha of I, y of I, x of I. And finally, all this, the derivative equals 0. From this one, we find out that omega equals sum over I of alpha I, y of I, x of I. This will become useful when we do the inverse transformation from dual to primal. And then that derivative according to the second parameter, the intercept, becomes wherever the intercept appears, we get it as if we are taking the derivative of x. Everywhere else it becomes 0. So this becomes 0, this becomes 0, and this becomes 0. So remaining this one, we take the coefficients, and that becomes a negative sum over I, alpha of I, y of I, and all equals 0. This gives us our new constraint that sum over I, alpha of I, y of I must equal 0. Now let's substitute the omega in the original objective function. So our new objective function becomes half. Remember that omega is a vector, x is a vector, so when we substitute for this squared value, we do it element-wise multiplication, sum of I, alpha of I, y of I, x of I, and then for the squared we sum over j, alpha of j, y of j, x of j. So we are done with this part. Let's convert to this one. This becomes negative sum over I, alpha of I, y of I, x of I, sum over j, alpha of j, y of j, x of j. So this part is done. We have got here these remaining two. Okay, let's have a look at our constraint. Alpha of I, y of I equals 0. That means this thing or this factor becomes 0. 0 multiplied by any variable is 0, so this whole variable becomes 0. So remaining only is sum over I, alpha of I. Let's make it more beautiful. Mathematics is always beautiful. So our objective function becomes sum over I, alpha of I. Now note here that these two factors are similar. It's same 1 over here, like 2 over 2. 1 minus 2 is minus 1. So this becomes minus 1 over 2. Now let's combine these two summations. Sum over I, sum over j, alpha I, alpha j, yi, yj, xi transpose xj. So note here that alpha is a single value, y is a single value, but x is a vector. That's why over here we find that this is a dot product of two vectors. So this becomes our final objective function we are trying to minimize to find the maximum distance separating the two areas or the two classes. Let's have a look at this equation. This is the objective function, the new objective function. Well, this is a quadratic programming, a convex quadratic program, which can be solved with the methods like Hansen's method. And it tells us one thing. It tells us that our algorithm or our equation depends mainly on the dot product between the samples vectors, on our feature samples. So if we try to maximize this distance, we have to do a transformation on the samples x that maximizes the distance. So for example, if we say that in the dimensionality or one Cartesian space, we've got x omega omega x. This is the famous XOR problem. It's hard to find a line that separates these two vectors. So how about if we transform them to a new space that makes it easy to do a separation like this by fitting a hyperplane over here that makes the separation too obvious. So in this case, we will have to replace the representation of our x with a transformation. So our transformation, for example, be transformation xi xj of two vectors. If we are talking about the linear transformation, that is what we have been doing, xi transpose xj. How about a polynomial transformation? That would be xi transpose xj plus 1 power p. And p over here is a vector or is a variable value that we can use as a parameter to fine-tune our quadratic program algorithm or the solver of the quadratic program. And another one is the Gaussian or the RPF. You will find it used interchangeably either as Gaussian or RPF, which depends on the Gaussian function as a transformation for the space between the samples. So simply we will replace the phi with the over the dot product here, and the equation goes the same way. So we have heard about support vector machines kernels. When we use a ready-made implementation for support vectors, then we always have to pass the parameter of the method a transformation, but we never understood where it comes from. So the motivation behind this mathematical derivation is to make it easier to make good reasoning about the kind of kernel function you are going to use for your support vector machine. So having done all this, what is remaining? Remaining is the constraints. So we know that the constraints in this case, so subject to, so this is our objective function, subject to alpha of I is greater than 0 and less than a value c. C is also a parameter for the algorithm. In scikit-learn, for example, you pass C and it helps in fine-tuning the performance of the quadratic programming solver. Usually it is Hansen methods. And the other constraint, it comes directly from the derivation here, is that sum I alpha I y of I equals 0. So having this done, we have converted our objective function from primal to dual, solved the quadratic program, got the coefficients and the parameter c and so on using a method for convex quadratic programming. How do we convert it back from dual to primal? That turns out to be very easy. You see over here, we have already got our omega. In case of using a kernel function, this becomes omega equals sum over I, alpha of I, y of I, phi of x of I. How about b? Can we find b? This is also obvious. We see over here omega x of I plus b equals y. So to find b, we simply solve the line equation. So b should become y of I minus omega x of I. And then for I from 0 to n, we add the summation over here over I to n. So this is in the case of a linear kernel function. How about the case of a transformation where we have used another transformation? The equation is slightly different, but again it comes by substituting this value or this equation for omega. So it becomes sum over I to n y of I minus sum, let's change I to j, so sum over j alpha j y of j, the transformation of xi xj, and voila, here we've got our omega, the slope, and here we've got our intercept b, and this or what is needed to define the support vector machine equation, the hyperplane that separates the two classes with the maximum difference. So this is the mathematics behind support vector machines. It's worth mentioning that support vector machines were first introduced by a mathematician, a Russian mathematician in the Soviet Union in 1962, and were not implemented till he moved to the United States in the 1990s, and then he introduced the algorithm to his colleagues in IPM. And to your amazement, the support vector machines at the time exceeded the state-of-art techniques of neural networks in solving the popular problem of MNIST classification, and got much better results than neural networks. Of course, at the moment we usually go to deep learning, but if the problem doesn't need that complex solution, then I find support vector machines very useful, very handy, and very practical in most of the situations. I hope you have enjoyed this recording. See you next recording. Thank you.